Okay, so for this problem, they're asking us, we have two cylindrical capacitors, in which case their equation is going to be C equals 2 pi epsilon naught L divided by the ln of R2 over R1. This is going to be the bigger one over the smaller one, outer versus inner. That's going to be the capacitance. So we can actually solve that by the givens that we were given. So you already did these calculations ahead of time, but essentially we end up with a 2.62 picofarads on that capacitor just by plugging it into the calculator here. 2.62 for C1, and then for C2 over here we'll be getting 3.96 picofarads. And so that's going to be that capacitor there. Now, this is pre-inflation. So essentially the problem is going to have us inflate this capacitor. And so we're going to make it C2 prime. And then we want to figure out, okay, well, how much electrons are going to be flowing through this point when we do that. In order to figure that out, we have to figure out how much charge change in order for the electrons to flow through that, right? So when we inflate this to the new R2, which is going to be 0.02 meters, I believe it was 2 centimeters, is the final state. So this is going to be like R2 prime here. That means that we'll have a new capacitor, and when we do that, we're going to end up with, basically, after doing the calculations in here, it should turn out to be like 2.6 picofarads. Right. But before we do any of that, let's also figure out what the charge is on these, and then figure out what the charge is on the second one. So first we got to figure out the charge. Let's combine these two into one capacitor. So like we'll have C12 over here. We're going to combine those two. Because they're in series, we have to do 1 over this. We're going to add the reciprocals together, and then we're going to figure that out. So when we do that, we've already done this calculation before. Comes out to 1.58 picofarads. All right, so that's going to be the combo of those two. Because we know the volts, we can multiply that together, and we're going to get, I think it's 15.8 picocoulombs in terms of the charge on the capacitor together. That's going to be distributed back into these two, so 15.8 picocoulombs on both of them. We're really only interested in the second one, so we could figure out we could figure out the voltage. It's not important though, because we're going to figure out what the new charge for the second one is going to be after we expand it bigger. So when we do that, we're going to actually come up with a new capacitor. Is going to be 1.3 picofarads. So that's going to be the capacitance of the inflated capacitor. From there, we can figure out the charge. Multiplying that by 10, we're going to get like 13.1 picocoulombs, essentially. Multiplying that by the 10 volts. That's going to be distributed over here. So now we know that the change of the charge was only 2.7. The delta Q equals 2.7 picocoulombs. And when we divide that by the electron number, 2.7 e to the negative 12 divided by 1.6 e to the negative 19, then we will get that the electrons that have moved through that are 16875,000. So that's 16 million or something like that. Okay, so that's kind of interesting. As far as the direction of where the electron's moving, apparently, if the charge is decreasing, considering this is negative, then they're going to be moving away from the battery. And if the delta Q is positive, then it would be moving toward the battery. So this is just kind of like some rule. I'm not too sure exactly why, but I guess that's what's going on here.